Good morning, students. So we are meeting again with another short session in carbohydrates. Today I am discussing the structure of fructose, open chain structure of fructose, followed by the cyclic form of the structure and then Howard structure of fructose. As you know, glucose and fructose both having the same molecular formula C6H12O6. I will take the camera and show you. First you will listen me and then I will show you the things which we have written on the blackboard. So the first one is a molecular formula C6H12O6, that is just the same as glucose molecule. Fructose molecule as glucose molecule in molecular formula basis both are the same C6H12O6. And we will find out we will study some of the reactions. And then we will be getting some of the conclusions. Based on those conclusions, we will write the open chain structure of glucose, followed by the ring structure and the Howard structures of fructose. I told you, glucose is a dextrorotatory compound. Fructose also naturally occurring fructose, that is known as fruit sugar. Fructose is nothing but it is known as fruit sugar, which is also actually optically active, and they are levorotatory compound. Optical rotation, I think the principal has started the classes so that you could understand what is dextrorotatory and levorotatory compounds. And fructose is a levorotatory, naturally occurring fruit sugar is a levorotatory compound. But there are examples of dextrorotatory fructose also. That is, synthetically if you prepare with fructose, then there is a possibility of dextrorotatory fructose also. But naturally they are levorotatory. And what is dextrorotatory, what is levorotatory, what is optical rotation? It is a property. Regarding that, I think the principal has already started the classes. Okay, let us see the reactions, some of the reactions, and let us find out the points one by one, and we will be adding the points to get the structure of the compound. First one is the molecular formula of the compound C6H12O6. Second one is the presence of a carbon chain. 6 carbon atoms is present as a chain in fructose also, which can be understood by the reduction of fructose molecule. If you produce the fructose molecule with phosphorus and hydrogen iodide, you are getting normal hexane. Normal hexane is formed from fructose molecule when it is on reduction. That is normal hexane. So normal hexane is a compound which can be written as like this, which you know. There is CH2, CH3, CH2, 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 1, 2, 3, 4, 5, CH3. So you can see this is a straight chain compound. You are getting a straight chain compound on reduction of fructose molecule, just like in the case of glucose molecules. The same reaction was there in glucose also, where you are getting a normal hexane molecule. Okay, next point is the presence of 5 OH groups. Just like in the case of glucose, the fructose also contains 5 OH groups, which can be studied by the reaction of acetylation, that is acetic anhydride. When you treat acetic anhydride or acetyl chloride with fructose molecule, you are getting a pentaacetate. Pentaacetate is formed. Glucose also was forming a pentaacetate, and fructose is also giving a pentaacetate. So 5 OH group present in the molecule can be confirmed by the reaction of fructose and acetyl chloride or acetic anhydride, forming a pentaacetate. That is acetylation. On acetylation you are getting a pentaacetate. Next reaction, presence of a ketonic group, CO group. CO group In the case of glucose, there was an aldehyde group, CHO group, here it is a CO group. That can be converted by the reaction with hydroxylamine. Hydroxylamine and fructose reacting together forming an oxime. So oxime is formed. So oxime is formed with hydroxylamine. So that shows fructose molecule contains a CO group. CO group is the carbonyl group. Right. The CO group it is present as a ketonic group in this case. CO group is present as a ketonic group in this case. That is also confirmed by the reaction of this fructose on oxidation. Fructose, if you oxidize, you are getting two acids. One is tartaric acid containing 4 carbon atoms and glycolic acid containing 2 carbon atoms. That means if any compound, any ketones can produce 2 acids, a mixture of acids on oxidation. Aldehydes can form only one acid. Ketone on oxidation, any ketones can produce 2 acids. That is, in this case also, tartaric acid containing 4 carbon atoms and glycolic acid containing 2 carbon atoms are formed when fructose is on oxidation. And I am talking some of the reactions which will give the idea of the structure of the molecule. And the next one point, the presence of CO group, where it is a long chain compound, we know, but having 6 carbon atoms, that also we know. There is 5 OH groups, there are 5 OH groups, that also we know. Presence of CO group, that also we can come to the point. And then ketonic group, CO group is present as a ketonic group, that also we can understood. And here, the presence of CO group, where it is there, that is at carbon number 2. Carbon number 2 it is there, that is confirmed by the reaction of fructose with hydrogen cyanide. You are getting cyanohydrine. Cyanohydrine on hydrolysis, you are getting a hydroxy acid. This hydroxy acid on reduction, you are getting 2-methyl hexanonic acid. So this reaction, that is the reaction number 6, in which fructose is on reaction with HCN, hydrogen cyanide forming cyanohydrine, and which is on hydrolysis, you are getting hydroxy acid, which is again on reduction, you are getting 2-methyl hexanonic acid. I will continue this after showing this reactions to a closer look. I am talking about the open chain structure of the compound. You can see the molecular formula of the compound, that is same as in the case of glucose, C6H12O6, and the carbon chain also just like same as in the case of glucose molecule, that is a chain of 6 carbon atom, and this can be conferred by the reduction of the fructose molecule forming normal hexane. You can see normal hexane I have written here, as you know, it's a long chain compound, CH3, CH2, 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 CH3. So you are getting the compound, that is this compound on reduction of the fructose molecule by using hydrogen and phosphorus in presence of hydrogen iodide. The third point is the presence of 5 OH groups. That reaction is based on the acetylation reaction, and you are getting a pentaacetate. That is, fructose reacts with acetyl chloride or acetic anhydride, forming a pentaacetate. Similarly, the point number 4, that is the presence of a CO group, carbonyl group, that is confirmed by the reaction of fructose with hydroxylamine forming an oxime. So oxime is formed, that is the point number 4. In point number 5, the ketonic group, CO group is present as a ketonic group, not as an aldehyde group. That is confirmed by forming 2 acids on oxidation. The compound is on oxidation, you are getting 2 acids. Only ketones can produce 2 acids when it is on oxidation. you are getting tartaric acid and glycolic acid. Tartaric acid contains 4 carbon atoms and glycolic acid containing, it is having 2 carbon atoms. 4 plus 2 is equal to 6. So there are 6 carbon atoms there. And point number 6 is the CO group is at 2, carbon number 2. That is confirmed by a series of reactions. That means the fructose is on reacting with hydrogen cyanide, you are getting cyanohydrine, which is on hydrolysis, you are getting hydroxy acid, and which is again on reduction, you are getting 2-methyl hexanonic acid. So these are some of the reactions, basic reactions leading to the conclusion of the open chain structure of the compound. So let me continue again. Let me fix the camera here.